Cool. So, hello, my name's Ben. I'm over at Queen Mary University in London, and I'm going to be talking about Raphtory, a system that me and my two advisors have been building, which is looking at distributed temporal graphs and how we're building and maintaining them from a set of event streams. So I just wanted to give you a little bit of an idea of why we got to this point. So kind of some of the original distributed graph processing systems had this idea that you've got a big chunk of data on disk, you've got some chosen algorithm, so you load it in, turn it into your graph, you churn through in a couple of iterations, and out pops your result. And then if you say want to see how things have changed throughout time, you might have snapshots, once a day for the last X number of months. And again, you load all these in, build them into graphs, you get a set of outputs, and then these can, you can do some deltas between them to see how things have changed. And that's quite sort of coarse, and if you only have snapshots once every day, then you kind of lose what happens in between and so on. This is kind of improved with these stream-based graph processing systems, where you have some event source out in the wild. So some of the examples we've been looking at are like cryptocurrencies, mapping data, so people moving around cities, and obviously social networks. And then changes in these event sources can then affect your in-memory graph. So in the case of a social network, you might have a user joins the network, someone follows their friend, and so on. So these can all be inserted in. And then users of your system can then query this, they request processing and get their results back. So this is great if you want to do some analysis on the most recent version of the graph, or alternatively, if you've got some metric that you're interested in monitoring and then seeing how this changes over time. So what we were thinking is that, well, if you've got all these changes coming in and you have all these problems with trying to keep all your graph in sync and up to date, why don't we just try to keep all of the changes and build a full temporal graph? So this in some ways simplifies the way that we actually synchronize, but then also allows us to do things like comparing the newest state to all of the previous versions of the state, and then actually do proper temporal queries. So something like if you're doing a shortest path, it might be, I only want to go out on edges that are younger than the one I come in on, or alternatively, you might have, say, for, I don't know, planes flying around, edges only exist for a certain period of time, and you need to get there and get on that edge before it disappears. So with those ideas in mind, we come up with Raphtory. Our initial work was on kind of formalizing this temporal graph model and the update semantics, so how we add, remove vertices and edges, as well as updating a set of properties that they have, so a key value set of properties associated with them. How we actually distribute and manage this graph in memory, so we have a set of partitions which have a set of vertices and edges each. And then how we sort of stream all of these updates into these partitions and keep them in sync. And then we also provide this sort of Pregel-like temporal graph analysis model in which the user can request to do some analysis on the live graph, any point back in time down to the resolution of the actual timestamps on the data. So you could say, what does it look like last Thursday at 3:02 in the afternoon? And then actually look through ranges, so sort of hop throughout the whole history of the graph and compute these different metrics and see how they change. So I'll just go over a quick run through the architecture. So over here we have this data spout. So this is kind of how the user decides how to connect to the outside world. So this is something like, I want to read this file, connect to this database, listen to this Kafka stream or something along these lines. This goes into a set of graph routers. Effectively what a router does is it takes a user-defined function and what that raw input transfers into in terms of graph updates. So what is a vertex, what is an edge? If something comes in, this is actually an update to a property and so on. And then they forward it off to the correct partition manager or partition of the graph, which deals with that vertex or edge that are affected. And then, as this is constantly running and maintaining, users can submit analysis requests which talk to the partitions. So I'll go on to that in a second. So if we dive into one of these partitions, they'll have a set of vertices and edges, as I said, and all of these will then have some history appended to them. So in this case, this vertex was created at time 8, then had some update appended to it at time 14. And this edge was created at time 14, possibly while this vertex has an update, and was then deleted at some point later on. As we're split across several partitions, we use an edge partitioning algorithm. So this edge down here, because vertex 1 and vertex 2 are different machines, are actually split across the two machines, and you can see they're in sync. Right, so one thing that's really interesting about this type of history is that now all of our updates kind of become additive. So even if we have a delete happen first and an add happen after, as long as we keep this chronological list, we can just slot them into the correct position, so you always end up with the right graph. So this is kind of nice because if you have this problem of updates coming in the wrong order for a lot of other systems, you either have to drop them, ignore them, or you get an incorrect state in one of your partitions. So as an example of this, we may have, say, this edge add that comes in at time 14. Because partition manager 1 deals with it, because vertex 1 is the source node. So we insert that into the machine, the edge gets created, and the vertex 1 gets updated. We then synchronize across to the other node, say, hey, I've got an edge that I share with you. So that gets updated into vertex 2, and the edge gets created there as well. So that's all fantastic, everything's happened in the correct order, everything's brilliant. Well, what happens if, say, an edge gets added before we get a vertex? Well, in this case, we can create both objects. The vertex actually just becomes a placeholder. And then, so again, we synchronize, do everything exactly the same. And then if the vertex add comes in at a later point, we just slot that into the history behind. So then if this comes in with all the properties and all this sort of interesting metadata about that vertex, it can be inserted at that point. And then obviously things can go completely haywire. So for some reason, some packets have been lost, or the network's gone all over the place. And in this case, this vertex has actually been deleted before it's even been created. So in a lot of systems, you might find that this is just, okay, well, this is nonsense, let's just drop it and ignore it. And that's obviously not what we want to do here. So we have a placeholder object which holds its deletion. When the edge add, in this instance, comes into the other machine, it does what it does in that machine and then synchronizes across, at which point the vertex now gets its creation at the correct point, and we can insert this edge. And then because this vertex was deleted, all of its incoming and outgoing edges should be deleted so we don't have anything hanging, and that can then synchronize back. So even though this went sort of completely wrong, you still end up with the same state and the same temporal graph moving forward. So we've stuck in some watermarking so you kind of know when it gets to the point where this is safe to do, or if you want to, you can go with the approximate approach of just give me what's going in memory now. So on that point, I know this is a bit sort of whistle stop, but we'll pop onto the analysis. So the general idea is that the routers are constantly ingesting new information from whatever source you've specified, assuming it's unbounded, and then the partition managers constantly keep in sync with each other and wait for requests from an analysis manager. So the user says, hey, I want to run this analysis. Can I submit it? So this goes off. All of the partition managers will then go through their set of vertices, run this sort of vertex-centric algorithm, and then return to the analysis manager. An analysis manager can then say, okay, well, all of my vertices have either decided to vote to halt or another iteration is required, and this will go back and forth until it's happy that it's finished and the result can be returned to the user. So what can the user actually request? Well, the first thing is that if we have this temporal graph in memory, we can say, okay, well, give me what the live graph looks like. So this is the most recent version of the graph, either watermarked, as I said, so this is kind of the safe live graph, or alternatively, you could ask for the bleeding edge, absolute most recent version in which you have some error of proximity, so depending on what sort of use case you have there. Alternatively, you might say, okay, well, give me what it looked like last week, last month, a year ago, something like this, and these tends to be sort of stored in memory, so we'll build that view, and I'll go over that in a second. Or alternatively, if Raphtory's been running for a very long time, and you start to have to push the older stuff out of memory, then we can start loading some of those things back if you want to go back that far. We're also looking for ways of sort of offloading very old queries into a different set of partition managers, so that query that sort of doesn't interrupt what's going on in the most recent version of the graph. That obviously is future work. Cool. So if we then say we have this full history of everything that's been ingested from time 0 up until time n, so the newest update, we might say, okay, well, I want to see what the graph looked like at t10. And a good way of viewing that, what a view is kind of like a right-hand filter. So you say, okay, well, this is everything that's happened. I'm not interested in anything that's happened after this point, so let's just kind of get rid of that for the moment. So that you kind of get to see now what the graph looked like exactly at that point of time. And then that can be used for your analysis. But one of the things we found was that if you're looking at very large data sets that have been existed for years and years, then there's an awful lot of patterns that happen in the short term that kind of get hidden by this huge aggregate amount of data. So we added in something we like to call also graph windowing, which kind of is like the left-hand filter. And in this case, you're saying, okay, well, I'm only interested in things that have happened in this band of time. So it could be from this timestamp for the last day, the last week, the last month, and so on. And so then you can actually view these short-term patterns as well as long-term ones. And so for that, we actually offer windowing batches. So you can say, okay, well, start at this point, and then just decrease the size of the window down continuously until you've done all the ones I'm interested in. As well as these individual views, you might actually say, okay, well, I'm interested in this sort of range of time, so over the last year or something, and I want to hop through at some set interval, maybe an hour or a day. And again, you can do this. So we can say build a view at the oldest point, so time 4, and then we can hop forward to time 6, and the new view is generated, time 8 and time 10. So again, if you're doing these ranges, you can have all this windowing and window batching on top as well. So that's obviously sort of very theoretical, and sort of a concrete use case would obviously be very nice, as I imagine a lot of you are thinking. So one of the things here that we had looked at was a network called Gab.ai. Has anyone heard of Gab? Good. I wouldn't think so. So Gab is a Twitter clone. It's kind of this like right-wing forum, but they had an open REST API. So I downloaded all of their posts. So They're like the big free speech thing, so I don't know. I assume that's why it's open. But so I scraped them all between the end of 2016 up until mid 2018, and we then had a look at if we set a query running for that whole range of time and hopped forward an hour at a time. What do we see any changes in something like just something simple like the largest connected component? So for this, we then set several different window sizes. So we said, okay, have a look at a very small window, like an hour, a day, a week, month, year, and then the full aggregate graph. And the interesting thing here is that even though you're running kind of the same algorithm, you actually notice very different patterns. So the aggregate kind of shows, oh, the connected component continuously grows, whereas actually if you look at something like the month, you have these peaks of interest. So this is actually Donald Trump's election. This was the Charlottesville riots. So there's kind of like these like peaks of activity when people join the network and start using it, and then that sort of drops down again. And then if we zoom in a little bit further, down to the hour scale, you can see that everything above like a window size of a day, the largest connected component is always like 100% of the graph. So everyone's always connected. It doesn't really change very much. However, for an hour, you get this lovely diurnal pattern as people kind of go to sleep and wake back up. So the largest connected component, so is like 80% of the graph, so almost everyone is connected. But then as people start to go to sleep, this all breaks down into very small communities that are talking to each other in the wee hours. And then that brings back up again as people start coming back online. So yeah, so even doing the same query, running on these sort of different lenses or views of the graph, gives you very different results. So we're kind of starting to explore this a little bit now, and we're obviously interested in anyone that's wants to talk about this sort of stuff. So on that point, if you are interested in using Raphtory, it is available on GitHub. It's all Dockerized and has some actually pretty dreadful scripts to run it, but I'm working on improving those. So yeah, so you can run it in there. There's the examples of that the actual Gab graph that I just went over. We've got loads of spouts for ingesting different data. So Gab, Twitter, Bitcoin, Ethereum, and loads of other random ones. We have actually ingested the whole Bitcoin and Ethereum graphs over a big cluster of machines, and are working with a couple of different companies to do some like know your customer entity resolution stuff. And so yeah, and we also have multiple analysis functions, so things like connected components and PageRank. We're looking at information diffusion, so this is like spreading taint across cryptocurrency, and then simple things like degree ranking and so on. So for the future of Raphtory, we've just been funded by the Alan Turing Institute in London, for any of you guys that know it, to turn this from kind of the initial researchy project into an actual product that researchers can use. So we're partnering with the Leeds University to look at some very large transport data sets, mapping people moving around cities, and then so see how that changes over time. If the council do something like they put in a pelican crossing, how long do they have to monitor to see sort of different changes in foot traffic? And also we're now spinning this out of Queen Mary into a company called Choreograph. So if you do see this name pop up, then it's probably me, or not someone trying to steal my name. But yeah, if you are interested, please drop me a line, or leave anything on the Git. I'm always on there. So thank you very much for listening.
Do you have some time for questions?
Yep.
Can you achieve performance improvements by like taking snapshots?
So the question is, can we achieve performance improvements by taking snapshots? So do you mean for the actual processing side, or for the ingestion side of things?
For the processing side.
So on the processing side, we're looking at this a little bit. So with all the in-memory stuff, when you build a view, all of the previous versions are already there. So you just go to the vertex, you pull what it would look like at that point in time if it was, so you'd filter initially, and you then you can use that vertex as it exists in memory already. For the stuff that's pulled back in from disk, we're having a look at different snapshotting / replay mechanics to make sure that they work properly. So there'll be this kind of idea of, okay, every X minutes you take a snapshot, and then you have the replay of messages using Akka, sort of the message replay to say, okay, let's get back to exactly the point we're interested in, and then what's the sort of heuristics around that. So that's kind of the next step that we're looking at the moment. But yeah, so it's for everything that's in memory, it works pretty much as is. Yep.
If I've correctly understood you, you were thinking of I have one starting network and a constant stream of messages coming in from a single point of truth.
Yes.
Now, if you have a simulation environment where multiple people want to make different modifications of network and look at variants of your network.
Yes.
Is that something that we can handle?
So we're having a look at perhaps some sort of like I don't know, vector clock implementation or something where you get sort of different timestamps from all over the place coming in. For the moment, our assumption is that if you're attaching to an outside source, that's going to be the timestamps coming in are the timestamps we're using. So a lot of the ones, or say for example on the social networks, they tend to have, that's done within their servers. For the cryptocurrencies, that's done when the block is published. So for the most of our use cases, we've kind of focused on that. It'd be really interesting to see how we would do it, but I think for the moment it's not going to be so much of
My
a...
idea would be maybe you model some production, somebody says, okay, what happens if I place a production order here, and another person sitting in another office says, what happens if I place
Oh, I see what you mean.
order? And of course, this gives you variance of your production network, and
That's
but you
interesting.
don't want to keep full copies.
Yeah, no.
memory, but you want to keep these differences somehow.
I see. Yeah, so that perhaps some sort of rollback feature would be like if a sort of update that come in that shouldn't have come in was so we could. I don't know how we do it at the moment, but it's definitely something to consider. Actually, yeah, I will put in on my notes of things to add in at some point. Yeah, no, thank you very much.
Any more questions?
Okay.
What's the biggest challenge of implementing graph algorithms and these dynamic graphs? Or are there any things that you see from because you have this kind of constant flow of data
Yes.
into the graph, so is there anything that you do differently from implementing graph algorithms than you would do on a static graph?
No, so at the moment the kind of view is that when you build, if you're building a view which is kind of safe, so either it's been watermarked or is a previous point in time, then it's kind of just a static graph and that's fine.
Okay.
When it comes to so if you have got like you're doing analysis, so obviously it runs in parallel, but if you're doing analysis on the most recent version, you do have some degree of approximation. We're having a look at like if we can kind of work out what that degree is, or something around that. But we've only really just started working on the analysis the last sort of 6 to 9 months. So but yeah, no, it's definitely the next sort of frontier of it for sure.
Could you use this for pathfinding in dynamic environments? Things like for maybe like self-driving cars, but also maybe like in games that have dynamic environments. Or is it too slow for that?
So I guess the question is on can you use it for pathfinding in dynamic environments? So I think it depends on the sort of speed at which you're interested in. So and of course the size of the graph. So I think you probably could if you're going for like if you're interested in maybe around a couple of hundred milliseconds. I don't know if you're interested in sort of proper real time. It needs to be sort of microsecond or sub millisecond. It probably wouldn't return fast enough for something like that. But then it's been more optimized for sort of general queries throughout time, like the ones we were showing. So you kind of chunk it in, you leave it running, and it kind of goes forever. But again, if we had the data to have it play around with it, I'd love to give it a go.
Cool.
Cool.
Thanks very much.
Thank you very much.